All right, so one particular application or type of max-min problem is in economics, and we've kind of talked, we've certainly done revenue questions before, back in Math 20. Now our equations might not just be quadratic, and most times you're not going to need to come up with an equation. So things to remember, usually we use capital R for revenue. That's the amount of money that you collect for selling X number of items. Capital C is the amount of money it costs to produce X number of items. And capital P, difference between the revenue and cost, that's the profit. How much the difference is, that's considered profit. You can go and reinvest in the company or spend it or whatever. Then some other definitions. If it asks for marginal revenue, that's the amount of money collected from selling just one more item. So it's kind of like, if you think about induction, that next item. There's not many questions like that. Marginal cost is the amount of money spent to produce just one more item, and marginal profit, the profit earned from selling just one more item. So you're given a certain number of items, what's the cost for the next one? Okay, so since the profit is revenue minus cost, the maximum or minimum profit occurs when, obviously, the profit function equals, the derivative of the profit function equals 0. Okay, and we're going to assume that the revenue and cost functions are differentiable for x greater than 0. Okay, so that means if we take the derivative of the profit function, that's really r prime of x minus c prime of x. Okay, so really if you set that equal to 0, the derivative of the revenue function equals the derivative of the cost function, which sometimes might come in handy. We have an example here of just one particular revenue function, one cost function. If you think about what the profit function would look like, profit is revenue minus cost. So where these intersect, the profit's going to be 0, right? Because it's going to cost the same to make them as the amount of money coming in. So you would have your profit function would have x-intercepts there. If you think about what happens between that, the cost function is the solid one. So if costs are higher than revenue, you're losing money. Your profits are below, right? If the revenue is above the costs, then you're above, and then it goes back below. Okay, so that could be your profit. That's an approximation of the profit function here. Okay, and so if you think about here, this would be your maximum profit. Now, this is just a sketch. Oops. But if you think about this, first derivative equaling 0, if we're trying to find maximum profit, that's where the derivative of the revenue would equal the derivative of the cost. And so that means the slope of their tangents would be the same. So it kind of looks like I've done a decent estimate. So that would be there, and this looks pretty much parallel over there. For that same, I guess, it would be a little bit higher, if you think about it. Right? We're just estimating, but that's basically how that's going to come about there. Okay. So let's do a practice question here, an example. So we're given a revenue function, and we're given a cost function, where x represents the number of units in thousands. So sometimes that's done to make it simpler. Determine the number of units that maximize the profit. So remember, profit is revenue minus cost. Okay, so we want to take the derivative. So, oops, You might subtract those functions to start, or you might take the derivative of each one. Doesn't matter, okay? If I do the derivative of each one, it might be a little bit simpler functions. Kind of depends, but these look like polynomial functions, so either way is pretty straightforward. So the derivative of the revenue function is 9. Derivative of the cost function is 3x squared minus 12x plus 15. And so I can go 9 minus 3x squared minus 12x plus 15. Okay, factor out of 3. Okay. All right, so I'll set that equal to 0. Unfortunately, it doesn't look like I can factor it, so I'm going to have to use the quadratic formula. Okay, so there's no values of x that make it undefined. Okay, we're going to not have any negative x values. We'll keep that, obviously, 0 and above for this particular application. And so, two critical values, 2 minus root 2. So remember, root 2 is about 1.4-ish. So that's going to be, we can put that here. 2 minus 1.4-ish is 0.6-ish. And then 2 plus root 2. Okay, so putting a value in for x, maybe, so I said this would be like 0.6-ish, so let's do something like, well, 0.5 would be a half. So negative times a half squared is 1/4, minus 4 times a half is minus 2, so that's a 1/4 minus 2 is negative 1 3/4, plus 2 is a positive. So overall, that's a negative. And then 2 would work. So x equals 2. 4 minus 8 is negative 4, plus 2 is negative 2. A negative times a negative is a positive. How about 5? 25 minus 20 is 5, plus 2 is a positive, times a negative is a negative. Right? And so you're asked to determine the number of units that maximize the profits. So we're not choosing this one, that's minimize, we're choosing this. This is a local max. So that's your x value. and it represents units in thousands. So therefore, determine the number of units. There would be 1,000 times 2 plus root 2, because you won't have a calculator on a test, right? You could use it for now. It's really slow because I'm recording. Plus root 2, 3.41, blah, 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 times 1,000. So if you did have your calculator, that's 3,414 units. Okay. So turn over the page. Do a little bit more work in this one. Says, according to a market survey, Howard's Hamburgers has determined that the yearly demand for their hamburgers is given by this. So lowercase p is often used, that's what the textbook uses, for demand, okay? And really the demand is the price. All right, so complete the following table. So if x is 0, so 0 units, then the p function is, well, 0 goes in there, that's going to be 4. 2,000 units substituted in, that's going to be 200,000 units. So 800,000 minus 200,000 is 600,000. Divided by 200,000 is 3. 400,000, that would be 2. 600,000 gives you 200,000, so that's 1, and then 0. Okay, so the demand function is actually the price function. More hamburgers are sold as the price decreases, hence the term demand, supply and demand. Yep. The demand function. So that's the price of a burger, if these are however many were sold in the year. Okay. So Howard has determined that the yearly cost function for his hamburgers is this. Okay. So notice that cost is not just the cost of the burger. When you run a business, there's so many other costs, not just the items that you're making or selling, right? Because you have your building, your employees, your utilities, your equipment, all that kind of stuff. So that's kind of like the 125,000 here. So determine the number of hamburgers that will maximize Howard's profits. Okay, so this case, our revenue function is going to be however many burgers are sold times the price function, lowercase p. Okay, and then we have our cost function here. So you could, so you could expand this out, right? You could simplify by the 200,000, expand through by x. So that would be, what would that be? 4x minus 1 over 200,000 x squared. and then take the derivative of that. Then take the derivative of the cost function. Okay, so derivative is 4 minus, so 1 over 200,000 times 2 will be 1 over 100,000 x. Okay, then derivative of the cost function is just 0.42. So that means the derivative of our profit function will be revenue, derivative of the revenue, minus 0.42. So that'll be 3.58. I'm going to factor out negative 1 over 100,000. So then I will get positive x minus this times 100,000, which will be 358,000. So then derivative equals 0 will give the coefficient of negative 1 over 100,000 won't play a part in calculating the critical value. It will when we're doing our increasing and decreasing. Okay, so if we think about our profit function, notice how I'm using capital P. 0. So any value between 0 and 358,000, if I put that in here to the bracket back into the first derivative, I'll have a negative times a negative, which is a positive. And then if anything more than that, this bracket will be positive. So a negative times a positive is a negative. And so this will be a local max. All right, so then another thing to look at is minimizing the average cost. Okay, so if you think about the average cost, that would be the cost function, which has all those costs of the building, the employees, all that kind of stuff built into it. But to get the average cost of each item that you end up selling, you would divide by however many you sell. right? So the more you sell, those sort of fee costs that are always there, that don't change, however you may sell or not, will start to be lower because you're selling more. The denominator is getting bigger here. So to minimize the average cost, we want to take the derivative of the average cost, okay, and set it equal to 0. Any min or max, you want to find when the derivative equal to 0. But now it's the minimum average cost. So the cost function divide by x. Okay, so let's think about taking the derivative of that. It's the quotient rule. So denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Okay, so then if we set that equal to 0, okay, we don't look at the denominator, but that denominator tells us that we can't have 0, so it's not going to work if we have 0 objects, because you can't divide by 0, right? But if we set this equal to 0, then take a look. If I rearrange this, I get c of x equals x times the derivative of c of x. And if I look back over here, my average cost is c of x divided by x. So if I divide this by x, both sides, I actually get, I'm going to put the derivative on the left now, I get the average cost. So this tells me here, okay, that the minimum average cost is the same as the average cost. So there's no minimum. So really, you don't have to find the derivative of the cost function. Or vice versa, if you are asked for the average cost, you could find the derivative of the cost function. So it's kind of a special property, right? So it means that you don't actually have to do as much work depending on what you're being asked to do. So if you're asked to find the minimum average cost, okay, that's going to be the same as the average cost. So minimum average cost is the same as just calculating the average cost. Okay. So next page is exactly that. So you're given the cost function, determine the number of units that minimizes the average cost. Okay. So if we look back here, minimizing the average cost means that it's the same as taking that cost function and dividing by x. So this is the average cost here. Right, so I want to minimize the average cost. So two ways of doing this. So I can take the, so if I call this A, I'm just going to move this over here just a sec. All right, trying to anyway. Okay, just a sec. Let me just move this and call it A. So this is A for average cost. Okay, so to minimize, I can take the derivative of that. Oops, sorry. And set it equal to 0. So I'm going to do this in two different ways. So then I would have 0 equals 2 times x minus 3, so x equals 3. Three times 1,000, so 3,000. But we'll keep it as x value there. So when x is 2, that will be a negative. When x is 4, that would be a positive. So this is a local min. Okay. The other way is going back and doing this function here. So c prime of x, oops, sorry, wrong way. So c prime of x equals the average cost. So that would be 3x squared minus 12x plus 15 equals x squared minus 6x plus 15. And you can see that you get almost the same values. You just have to get an extra, you get x, right? So, sorry, you get 0. Okay, but really, for average cost, we can't have x being 0, right? It doesn't make sense. We haven't sold any, you can't get an average cost, right? In terms of the x there. So we would call that inadmissible, and then you can look at the same properties. Okay, so then therefore the number of units that minimizes the average cost, 3,000 units, minimizes, I don't think I spelled that right, the average cost. So you can take the average cost, take the derivative to find that local min, or you can use the equation, the derivative of the cost function equals the average, and get the same thing. Kind of easier to do the average cost and take the derivative of it, but either way works. And that's really it. So you are done this unit.